Hello everyone and welcome to the lecture. In the last lecture, we have seen incidence matrix of a graph, right? And in particular, we have made use of the incident matrix to determine whether chosen n-1 edges from the graph are forming a spanning tree or not. We have seen that the sum matrix of the incidence matrix, the determinant of the sum matrix of the incident matrix can actually tell you whether the chosen edges, n-1 edges, are forming a spanning tree or not. This where the n is the number of vertices. Okay. Today we will make a very nice application of it. What was our aim? Our aim was to prove matrix tree theorem. Any cofactor of the Laplacian matrix give the number of spanning trees. Okay, very good. So now before, so we are just basically one step away from proving this magnificent theorem. Yeah, but I need one formula before that. This formula is about the determinant of the product of matrices, and it was given by two great men, Cauchy and Binet. So let me state that formula first, and then we will go to the last step of proving our matrix tree theorem. Okay, so formula. So this we also call Cauchy Binet formula. Okay, so let me write it first. Okay, very good. So I think this was given in 1812. Okay, very good. So it is saying that let A be an n cross m matrix and assume that n is less or equal to m, and B be m cross n matrix and matrix. Okay, then determinant of their product is given by okay, so what you do, you take all possible subsets of 1 to up to m, okay, such that the cardinality of this set is n. Okay, then it is this. So determinant of A, where you take all these all possible rows. So maybe I just write 1 to up to n. Okay, so all these rows, basically full rows, and then columns corresponding to t. Okay, and you multiply this with determinant of B, where you are choosing now rows corresponding to t, but all the columns 1 to up to n. Okay, very good. Okay, so and then you, okay, I hope this is clear. Okay, so let us take one example of it. So example is this: suppose A is your some 2 cross 3 matrix. So this is maybe 1 minus 2 1 2 5 4. Then using basically, and B is some 3 cross maybe 1 5 3 2 minus 1 0. Okay, so what will be AB? So you just verify that determinant of AB is nothing but summation over. Now what you do, you take the summation over all subset of 1 2 3 1 2 3. So there can be, I mean, you can, and now you have to take subsets of size 2, right, because here n equal to 2. So this is basically, if you take this, so this will be nothing but summation over determinant of 1 minus 2 to 5. So here I have taken 2 as 1 2. Okay, then determinant of the same thing you do for this. You know, you take first 2 rows and all the columns. Okay, minus 1. Then what? Then determinant of maybe 1 and 3. You take 1 and 3 column 1 2 1 4. Now similarly you have to take 1 and 3 row from B. So this is 1 2 3 0. and the last term is, maybe now I can actually ignore this part. Yeah, so because in any case I am doing the addition. Okay, so yeah, very good. So now, and the last thing was this minus 2 1 5 4, right, and determinant of 5 minus 1 3 0. Okay, so just verify that this is correct. Okay, very good. So now how can we make use of this formula? How can we make use of this formula? We will see a very elegant use of this very shortly. Okay, so what we have to prove? We have to prove that the any cofactor of Laplacian matrix gives the number of spanning trees, right? So let me take by default, so your Laplacian matrix is this. Okay, so suppose this is Laplacian matrix L11, L12 up to L1n and Ln1, Ln2, Lnn. This is n cross n matrix, and any cofactor of this will give. So we have to prove this, right? So suppose I by default, and we have proven that any cofactor is same. Okay, the same value is nothing but equal to the number of spanning trees that we have to prove. Okay, so let me pick the cofactor corresponding to the last basically Lnn entry. Okay, so I will delete its row and corresponding column. Okay, then the determinant of this matrix will be at number of spanning trees. We have to prove this. So let me actually denote this by now. Basically now from L I am removing the last row and the last column. Remember the notation I gave in the last lecture, and determinant of this matrix. Okay, so determinant of this matrix. Now how can we write Lnn? Basically removing the last row and last column. We know that the L is nothing but Qg into Q transpose. I am not writing G, so it's Q into Q transpose. This is now L1nn is what? Lnn is what? It's nothing but from Q you remove the last row and then multiply whatever the resulting matrix is with its transpose. Okay, so basically it is nothing but, so from Q you are removing the last row, so suppose now rows are just like this, n minus 1. Okay, suppose in Q there are, so basically in the graph G there are n vertices. Let me write it again, and m edges. Okay, and then how many rows I have to, I have to take all these rows, right? 1 2 up to m, right? This is Q, and whatever this is, you actually now multiply with this, its transpose, basically this. So Q, the same thing, 1 to n minus 1. Okay, and then same thing m. Okay, and transpose of it. Okay, it's basically it follows from this. So this is equal to that. Okay, now I have to find the determinant of it, right? Determinant of it. Remember, there will be a sign when we take cofactor here is minus. There will be a sign rule n plus 1. So this is even by default. So I am not actually writing it. Okay. So how can we make now use of this? So basically this matrix, and I have to take determinant of this. Okay. Now immediately you will realize that, oh, this matrix, if you see that, can I treat this matrix as A? Okay. Can I treat this matrix as B? And then maybe I can make use of Cauchy-Binet formula, right? A is what? N minus 1 cross M matrix. B is what? M cross N minus 1. Right? This is a transpose, so it will be that. Okay. And yes, indeed, we will make use of Cauchy-Binet formula very elegantly. So how can we write actually now? This is nothing but, so I can write this term as, so if you see carefully, you assume that this is A, this is B matrix, right? Now I will take basically the summation over all possible, so this is nothing but, if you take, let me write here in more better way here. So summation over all possible t, and this t is actually subset of 1, 2 up to m, such that t I will take of size n minus 1, from the Cauchy-Binet formula, because now Q has size n minus 1, the trimmed Q has size n minus 1, so this will be n minus 1. Okay, now what? Overall possible this, I will now make the basically make use of determinant of some matrix. So this is nothing but determinant of you take all the possible rows, so these are n minus 1 rows, and then take T is actually kind of choosing n minus 1 edges. We are choosing n minus 1 columns, but columns are corresponding to the edges, right? So it's like choosing n minus 1 edges from the graph. Okay, and then in fact the determinant of Q. Okay, so let me write it once again. So this is, yeah, this is good. So this matrix is of so maybe right, this is Q. Okay, so Q matrix. Okay, now times the determinant of this matrix, right? But these two are basically transpose of each other, so maybe I can again write the same thing, times determinant of Q again, and then I will write this, all these rows, n minus 1 rows. Okay, columns corresponding to basically n minus corresponding to T. Okay, so the T has size n minus 1, and transpose of it. Take transpose of it, because this is transpose. Okay, now we know that the transpose of the determinant the determinant of a transpose of matrix is same as its determinant of that matrix. Okay, so this quantity actually we can write as very easy, summation over again the same T, which is subset of M, and the cardinality is n minus 1. It is just like choosing n minus 1 edges. Okay, now this is nothing but determinant of some matrix. Yeah, so like Q 1 2 up to n minus 1 rows here, and columns corresponding to T. Okay, so maybe I can write this, and then oh, okay, actually I am just making slight unnecessary thing here, so this may not be this, so this, yeah, this is correct, this is okay, so very good. So now here, yeah, so very good here. Okay, now this is nothing but square, because these two quantities are same, right? Now we know that. Now what is this quantity? If you see the last theorem in the last lecture, okay, this quantity will give you plus or minus 1 only when the chosen n minus 1 edges are forming a tree, right? Plus 1 or minus 1, and you are taking a square of that, that means it is equal to 1, right? When the chosen T or chosen n minus 1 are forming a spanning tree, otherwise it is giving 0. So this will be nothing but total number of spanning trees in the graph. Okay, very good. So this proves that this is nothing but total number of spanning trees in the graph. Very nice result. Okay, very good. So I hope you enjoyed the proof of it. It was slightly involved, but very simple one, slightly counterintuitive, but you need very basic knowledge about the determinants and all, and you have proven this. Very good. So now there are actually very nice implications of this result. Okay, remember in the beginning of when I was stating that magic or the matrix tree theorem, I told you why the approach of choosing every time n minus 1 edges and deciding whether these n minus 1 edges are forming a tree or not, right? This is not an efficient approach. Why it is so? The reason is because there can be many subsets of size n minus 1 out of m. M is the number of edges, right? But why this determinant thing is giving efficient? Maybe this determinant is very complicated or very inefficient to calculate. Fortunately, we can compute the determinant very efficiently. In fact, the time complexity, those who do not know time complexity, it's just like finding the number of basic operation an algorithm does to find the answer. For example, your matrix multiplication. So you are picking, so what is the time number of operation like addition, multiplication and subtraction to compute the matrix product of two matrices. You just check that, it will roughly come out to be order of n cube by our school method. Okay, but the surprising fact is this: the time complexity, the asymptotic time complexity, basically when the n is very large, the asymptotic time complexity of matrix product and determinant is same. Very elegant result. That means you can indeed find the determinants in whatever the time complexity is of matrix product. Currently, the fastest matrix products takes order of n to the power 2. I guess something 2.376 if I am correct now. So you can indeed find the matrix this matrix determinant also in order of n to the power 2.376. Okay, one intuition I will give you how this is possible. Remember our basic linear algebra classes, right, where how we can find the determinant for any matrix, any square matrix, right? You can always decompose this matrix into lower triangular matrix and upper triangular matrix using Gaussian elimination. Sometimes we need to reorder these basically the columns or rows, okay, to give this form, okay, but this can be done for any square matrix, and after that we can make very elegant use of determinant property. The determinant of basically this can be written as determinant of this, right, which is, let me write it more precisely, determinant, okay, so this is nothing but determinant of A times determinant of P, determinant of L times the determinant of U. Okay, determinant of L is, it's a lower triangular matrix, nothing but determinant is just a product of diagonal entries. Similarly, determinant of U is upper triangular matrix, its determinant nothing but product of its diagonal entries. So very simple, no need to do that basically this expansion or what we call Laplace expansion, which is very costly. Here you can immediately see. And by the way, determinant of P is nothing, P is some permutation matrix which is nothing but there is an identity matrix, and you are basically shifting ones on the diagonals to the above, lower. So basically, and at each row and each column still there is just one, okay, and determinant of some matrix is either +1 or -1. Okay, very easy to calculate. So basically these things are easy to calculate, this is easy to calculate, hence determinant of A is in fact basically either plus minus okay, so basically the aim is to make you realize that determinant can be easily calculated. Okay, and by the way, this decomposition A and P equal to L and U, this you can do using Gaussian elimination. But thus it's just actually some basically the product of elementary matrices. You have to make some matrix product with A by some elementary matrix, and it will automatically convert to L and U. Okay, so the basically time complexity of calculating determinant is same as time complexity of calculating matrix product. Very basic fundamental thing and very elegant thing. But now let me relate this question of finding number of spanning trees or equivalently finding the determinant in terms of some another problem. okay, some another question, very similar looking question, okay, but solution there is not at all the same. Solution is, I mean, finding the solution is extremely different. Okay, so let me first tell you something similar quantity to determinant that we call permanent. You can treat that quantity as maybe brother of determinant. So let me take an example of 3 cross 3 matrix. Okay, suppose we have a 3 cross 3 matrix, this A, B, C, D, E, F, G, H, I. Okay, what is its determinant? Determinant is this. Okay, A, E, I. So now here I am actually making use of Laplace expansion just to show what will the value of this. A, E, I minus A, F, H, and then minus B, G, F, then plus B, D, I, and then maybe there will be 2 more terms. So this will be plus C, D, H, minus C, E, G. Okay, now there is, so this is determinant. There is something called permanent. As I told you, this is like brother of determinant, which is nothing but for the same matrix. This is nothing but you replace the negative signs with plus. Okay, and that's all. Okay, so basically every sign here is plus now. A, E, I plus A, F, H plus B, G, F plus B, D, I plus C, D, H plus C, E, G. I hope I have written it correctly. Now question is, suppose I give you a very large matrix, suppose n cross n, maybe 100 cross 100 matrix, right? Now determinant, I already tell you how we can calculate using LUP decomposition. Okay, what about the permanent? Unfortunately, there is no polynomial time algorithm to compute the permanent. In fact, there cannot be any polynomial time algorithm for computing permanent unless until the famous conjecture in computer science, P is equal to NP. Let us not go into detail of that. Okay, so you just realize that this is not possible. This is not looking possible as of now, and it's basically very difficult for our computers to compute the permanent, even for 0-1 matrices. If you take just 0-1 matrices, okay, computing permanent is extremely challenging task. Okay, now let me relate, like the determinant can be related with finding the number of a spanning tree. Now similar thing let me relate with permanent. Okay, so suppose I take permanent of a matrix, suppose just 0, 0, 0, where there are only 0 and 1s. Okay, so suppose this 1, 1, need not to be symmetric matrix, you can take any one. Okay, and now I make a graph out of it. Let me make a graph out of it. So this is 3 cross 3 matrix. Okay, the graph is suppose this. There are 3 vertex I am putting here, 3 vertex I am putting here. Let me number them 1, 2, 3, 1, 2, 3. Now based on the entries in this matrix, I will make edges here. So 1 is not connected to 1 basically because of 0. Now 1 and 2 has 1 here. So 1, 2th entry has 1. So let me make an edge with 1, 2. Similarly 1, 3. Then 2 is will have edge with every 1. Okay, and 3 will have edge with 1 and 2. Okay, now this is, we will see that this is kind of bipartite graph where there are 2 set of vertices. Inside any set there is no edge, all the edges are going from one set to another set. Okay, this is a very famous graph. Okay, now the question is about something called matchings in bipartite graph. Matchings are nothing but, I mean, these are set of disjoint edges. For example, here this. Okay, like here. Okay, a matching is called perfect matching when the set actually covers all the edges. But is there a perfect matching? Yes, indeed. Suppose if I take these 3 edges, these edges are actually covering all the vertices. These 3 edges are disjoint and also covering all the vertices. Okay, This is called a perfect matching. Okay. How many perfect matchings are there in a given bipartite graph? This is also very challenging question. In fact, if you see that there is actually 1-to-1 correspondence between these two questions, finding number of perfect matchings in a given bipartite graph and finding the permanent corresponding square matrix. So here actually my bipartite graph is, you can say, balanced bipartite graph when both sides there are equal number of vertices. This is, you can easily establish that corresponding to every perfect matching there is something, basically some of these terms, there will be some terms, right, corresponding to each perfect matching, and similarly corresponding to some term here there will be a perfect matching. So there is 1-to-1 correspondence between the perfect matching and these product terms here. Okay, so these computationally both of these problems are equivalent, and like computationally finding the number of spanning trees is same as calculating the determinant. Here finding the number of perfect matching is same as finding the permanent of the corresponding square matrix. So if you see that, and by the way, at a first glance it looks like if I had asked you what is easier to solve, determinant or permanent, you might be thinking that, oh, in the case of determinant there are plus and minus signs, we have to take care of minus signs, but in case of permanent there are no minus signs. So maybe permanent is as easy as calculating determinant, but the reality is extreme. The reality is actually quite different. Permanent is actually something called Sharpe complete problem, whereas determinant can be solved in polynomial time. It's same as you can find the number of spanning trees in polynomial time, but finding the number of perfect matching even in bipartite graphs is very challenging. It's again Sharpe complete problem. With this I am stopping this lecture. So thank you very much. I hope you have enjoyed this, and see you in the next lecture.